All right, this is page 39 of math analysis. We're still talking about graphs of sine and cosine. We just want to generalize some of the features, make sure that you notice some things. So I use GeoGebra, which I would definitely encourage you to check out. So I use GeoGebra, geogebra.org, and then I always use the classic GeoGebra to graph things. But I use it to graph these. It makes very nice graphs. They're really easy to insert into things, and that's what I really like about them. But I use it to graph sine and cosine. And what we want to do is just identify some patterns, some things like that. So for patterns, let's start with sine. And when we talk about the pattern, we're always starting at 0, right? Because that's where sine starts. That's where the unit circle starts. And it's really based on the unit circle. So I'm going to say the pattern is I, M, I, M, I. And then it just keeps repeating forever, right? So we went I, M, I, M, I. And if I kept going, I would just go up to capital M again, a maximum, intercept, minimum, intercept, maximum, intercept, minimum, intercept, max, and you just keep going forever. Cosine, kind of similar, but because cosine is the x-coordinate on the unit circle, I forgot what I was writing. Because it's the x-coordinate on the unit circle, it starts at 1 when theta is 0, and then it decreases from there. So cosine is going to go from a maximum to an intercept to a minimum to a maximum. And I don't know if there's any other patterns I really want to talk about here. I mean, you have you have a maximum starting at 0, then at 2 pi, so you have a maximum at every 2. So let me just write that. We have a max at x equals 0 plus, we keep adding 2 pi times n, but if you remember, we have to make n an integer, so we do this. Well, what about the minimums? Those occur at, there's one at pi that we can see, there's one at negative pi, so it looks like the minimums are going to be at x equals pi plus 2 pi n, but of course n is an element of the integers. So that's pretty good. Now, I guess we should go back and do the same thing here. So intercepts, right? So those are going to happen at 0 plus pi times n for sine. But I want to do the maximums and the minimums. So maximum is going to be at x equals, where's the first one you see? I see pi over 2. And then because the period we talked about is 2 pi, they're just going to repeat every 2 pi. So plus 2 pi, whoops, 2 pi n, where n is an element of the integer. Oh God, that didn't go well. N is an element of the integers. Got to squeeze it in there. Now the minimums, find a minimum that you can see. I see a minimum at 3 pi over 2. And then the period of sine is 2 pi, so it makes sense that there's another one at negative pi over 2. Subtract 2 pi from 3 pi over 2 and negative pi over 2. And say x is 3 pi over 2 plus 2 pi n. N is an element of the integers. So n can be negative because the integers can be negative. So the next thing we want to talk about is the shape of the curve. So I don't know how much we want to say about this. I'm going to say, so I'm going to talk about something called concave up and concave down. So here, and I'm just going to highlight, I think. So initially, on this part of the curve, if I were to put a line on the curve, it's called a tangent line. It's going to intersect it at one point and then kind of have the same slope. You can see that this tangent line is above the curve. Anytime the tangent line is above the curve, or the curve is kind of curving down away from the tangent lines, the curve is called concave down. So what I'm going to say is that, what can we say about that? I mean, I'd like to talk about that. So I will say that in the first period, so that's between 0 and 2 pi, sine is concave down, C-O-N-C-A-V-E, concave down for 0 to pi. And then, so concave down means curving down. It's kind of bending down away from the tangent lines. If we switch between pi and 3 pi over 2, you will notice that if we put a line on this, the curve is bending up away from it. It's concave up in that case. So from pi to 2 pi, the curve is concave up. And so sine is concave up. So concavity is something you talk about a lot in calculus. And the sooner you like get introduced to the idea, I think the better, which is why I'm talking about it now. This is not like a big deal that you're going to talk about a lot involving these curves, but it's good to know about it, right? So always picture like, what if I put a line on this thing and just kind of like let it go? It'd be like if you drove a car on this, where are the headlights, right? Are the headlights above the curve? Are they below the curve? Like what is going on? So that's what's happening there. And then should we talk about it for cosine? Cosine's a little harder because so concave down to start and to end. So that's concave down, and then concave up from pi over 2 to 3 pi over 2. So let's try to write that down. So cosine is concave down. So I'm starting with concave down because it starts concave down. But we can't do it in like one continuous thing. So we'll say 0 to pi over 2, and then 3 pi over 2. But for half of the period, right? For like an entire pi radians, it's just like a disjoint pi radians, whereas sine, it's a continuous pi radians in that first interval. But that's okay. Because things happen. We don't get to control that. Concave up for pi over 2 to, what am I doing? 3 pi over 2. Yay. Okay, so we get this. Now that's like the least important feature, I would say, from our perspective. Now the relationship, what did we say? So I think that if I take the cosine graph and I shift it, right? Just take the entire graph and move it this way by pi over 2, by just pi over 2. I think that I will get the graph of sine. I think that that's happening. So I want to shift it pi over 2 to the right. So I think that cosine of x looks like it's equal to, forgot that. It looks like it's equal to the graph of, what did I want to do? I wanted to shift cosine. So if I shift cosine of x minus pi over 2, so this shifts it pi over 2 to the right, should be equal to sine of x. Well, that's like really interesting because that is almost the cofunction identity. Now, cosine is even, which means that the cosine of negative theta equals the cosine of theta. So from here, I could say that the cosine of, let me factor a negative out and get negative pi over 2 minus x is equal to the sine of x. And then let's use the fact. So this, we're going to use this and say, therefore, sine of x equals cosine of pi over 2 minus x. Definitely true. It's definitely true. I mean, look at it. Like if we take cosine and we shift it pi over 2 to the right, we will get sine. But I could just as easily have shifted it pi over 2 this way, and I would almost get sine, but I would not get sine by doing that. What would I do instead? I would actually get negative sine. I don't want to talk about that. So that was a mistake on my part. I didn't want to do that. If I took sine and I shifted it pi over 2 in which direction? If I shift the sine graph this way by pi over 2, I will get a cosine graph. So let's say that I mean, I guess a new color is in order here. So if I shift sine, so cosine of x is equal to sine of, I want to shift it pi over 2 to the left. So that's actually plus pi over 2. And that's totally true. You can use any of these sorts of things. I think we prefer this, right? So if we think about the sine one, it should be the case that cosine equals sine of pi over 2 minus x. So what would that mean? Well, sine of, let me move this a little bit. Move this up here. I'm out of my table, but that's okay. Sine is an odd function, so cosine of x. Do the same sort of thing. Sine of negative quantity, x minus pi over 2. Okay, and then sine is odd, so cosine of x equals the negative of the sine of x minus pi over 2. So what's this telling me to do? It's saying shift it pi over 2 to the right, and then reflect it. Shift pi over 2 to the right. I'll erase this, but I'm going to try it. Shift pi over 2 to the right. So this point is going to go here, here, here. But I'm supposed to reflect it. So what else has shifted? This point has gone over here. I'm going to erase all of these in a second. And then this point goes here, but then reflect. So the reflection, there. Yeah, yep, that's cosine. That's cosine for you. It does it. So I need to erase all of that because it's messing up my figure. But there you go. All right, anything else? I don't know that there's anything else that we need to really say about these. They come up all the time. We got to get really good at using them, recognizing them. The patterns are a big, big deal. I mean, you have to have those memorized. So make sure, concerted effort. Think of the unit circle. How does the unit circle start, right? At 0, you are at the point 1, 0. So cosine is 1, sine is 0. Cosine is 1, sine is 0. So look at it. Cosine is 1, sine is 0. And then we know how the unit circle works. If you start at 1, you're going to have to decrease. We know that we're going counterclockwise, so the y-coordinate increases, the sine graph increases. It's all related. I'm going to stop this here. And actually, I guess for the sake of filling it in, I'll say, nope, I think we're good. That's always just in case when there's like 30 people calling out things, you never know. But here, since I'm by myself, you kind of do know. All right, so I'm going to cut this here, come back, finish this page, do some other stuff. So I will see you then.